The chain rule is really a much quicker version of U substitution. When you're going to use the chain rule, it's important to identify what's on the inside and what's on the outside and kind of work your way through the problem that way. When I look at y is equal to the natural log of the square root of 3x minus 5, the first thing I would do before I even started thinking about U substitution is probably to write it with a power instead. I like having, instead of having square root of 3x minus 5, I would rather have x minus 5 to the 1/2 power, because powers are a little bit easier to deal with. Also, I notice that I have parentheses embedded in other parentheses. So it's a lot easier to see that this 3x minus 5, that's like the innermost part of the function. Then the next part is going to be that 1/2 power, and the last thing is going to be the natural log. So that's the outside of the function. Then, when I take the derivative, I'm going to start on the outside and work my way in. So the derivative of y, first thing I look to is the natural log, right here. The derivative of the natural log is 1 over. So 1 over everything that's there. The 3x minus 5 to the 1/2 power. The next thing I'm going to deal with is the power, 1/2. And how we deal with powers is we bring the power down. So I'm going to multiply by 1/2 times 3x minus 5 to the negative 1/2 power. So we bring the power down and reduce the power by 1. So this is the derivative of that next part. The last piece we have is this 3x minus 5. And the derivative of 3x minus 5 is just 3. So now I have a correct derivative, and the only thing left to do is really just to clean it up. So what I notice is that this derivative has a fraction in it, so I'm going to kind of keep the fraction. In the first fraction, I have the 3x minus 5 to the 1/2, so I'll put that down here. Then I have 1/2, so that would put a 2 as a coefficient in the denominator. The 3x minus 5 to the negative 1/2, that goes in the denominator and becomes a positive 1/2 power. And the last thing is that 3, which would go in the numerator. We can clean this up a little bit because I do have this 3x minus 5 to the 1/2 and 3x minus 5 to the 1/2. So when you multiply exponents, you add their powers, meaning that my denominator will be 2 times 3x minus 5. And we can clean that up a little bit too, into 3 over 6x minus 10. So let's find the derivative of y equals secant to the 5th of x. It might be helpful to rewrite this as y equals secant of x to the 5th power. This way it just kind of really emphasizes what function is on the inside and which one is on the outside. When we see it like this, we can definitely see that the secant is the interior function, and that 5th power, that's what's on the outside. So when we want to take the derivative, using the chain rule, we work from the outside in. My outside function is that power, so I'll bring the power down and then reduce the power by 1. The base is just going to be the secant of x. Then we'll multiply by what's on the inside, the derivative of secant of x, which will be secant times tangent. Trying to clean this up at all, I do have a secant to the 4th times another secant, so we can combine that and be left with secant to the 5th of x times tangent of x, and that will be the derivative. So far, when we've seen functions embedded in other functions, it's been very helpful to rewrite the function in some other form. In this case, when I have 10 to the 1 over x, looking at 1 over x as x to the negative 1st power makes it a little bit easier to identify what function gets done first and what's next. So thinking about plugging a value in for x and then calculating it by hand, I would have to plug a number in for x and then take it to the negative 1 power first. that would mean that negative 1 power is the interior function. After that, you would use that value as the power for 10 to the x to the negative 1, meaning that this base of 10 is the outside function. So now that it's time to find the derivative, we work from the outside in. Since the outside is the exponential with a base of 10, that means we're going to keep the 10 to the x to the negative 1 and multiply it by the natural log of 10. That takes care of the base of 10. Next, we'll take the derivative of the interior function, negative 1 x to the negative 2. At this point, we can clean it up a little bit, but this is perfectly fine. I would probably bring the negative 1 along with the coefficient of natural log of 10 out in front. So negative natural log of 10. Because natural log of 10 is, it's just a number, it's a coefficient. Then anything that has a variable would end up coming after the coefficient. Because this x to the negative 2 has a negative 2 power, I could create a fraction, putting that x squared in the denominator, and in the numerator, we would be left with just the 10 to the x to the negative 1, which from the beginning was 10 to the 1 over x. There's really not much else, nothing else that I can do, and so that's going to be our derivative.